We've already talked about how to write an equilibrium expression. So if we have some generic acid HA that donates a proton to H2O, H2O becomes H3O plus, and HA turns into the conjugate base, which is A minus. And so here's our equilibrium expression, and the ionization constant Ka for a weak acid, we already talked about the fact that it's going to be less than 1. So here we have 3 weak acids, so hydrofluoric acid, acetic acid, and methanol. And over here are the Ka values. So you can see that hydrofluoric acid has the largest Ka value. So even though they're all considered to be weak acids, right, 3.5 times 10 to the negative 4 is larger than 1.8 times 10 to the negative 5. So hydrofluoric acid is stronger than acetic acid, and acetic acid is stronger than methanol. But again, they're all considered to be weak acids relative to the stronger ones. So let's talk about pKa. So the pKa is defined as the negative log of the Ka. So if we wanted to find the pKa for methanol, all we have to do is take the Ka and take the negative log of it. So the pKa is equal to the negative log of 2.9 times 10 to the negative 16. So let's get out the calculator and let's do that. Negative log of 2.9 times 10 to the negative 16. And this gives us 15.54. Right, when we round that. So the pKa of methanol, the pKa of methanol is equal to 15.54. So we could write in a pKa column right here, and for methanol, it's 15.54. If you did the same calculation for acetic acid, you would get 4.74. And once again, if you did this for hydrofluoric acid, you would get 3.46. So as we go up on our table here, right, we're increasing in acid strength. So out of our 3 weak acids, hydrofluoric acid is the strongest, so it has the largest value for Ka, but notice it has the smallest value for the pKa, right? So the lower the value for pKa, the more acidic your acid. So 3.46 is lower than 4.74, and so hydrofluoric acid is more acidic than acetic acid. The problem asks us to calculate the pH of a 1 molar solution of vinegar, which is acetic acid in water. So let's start by writing our acid-base reaction. So we have acetic acid, so CH3COOH, plus water, and if acetic acid donates a proton to water, water would turn into H3O plus, the hydronium ion, and we would also get the acetate anion, CH3COO-, the conjugate base to acetic acid. So before we get to this problem, let's just pretend that we're starting with 100 molecules of acetic acid. So 100 molecules of acetic acid here. And let's say none of them have reacted. So this is before any reaction has occurred, which means we don't have any of our products, right? We don't have any hydronium ions. We don't have any acetate anions. And acetic acid is a weak acid. If a strong acid would ionize 100%, so all 100 of those molecules pretty much would ionize. But since acetic acid is weak, let's pretend like only one of those acetic acid molecules donates a proton to water. So we're going to lose 1 molecule of acetic acid, and that's going to turn into the acetate anion. So if we lose 1 molecule of acetic acid, we gain 1 acetate anion. And therefore, if we protonate 1 molecule of water with that proton, right, we're going to gain 1 hydronium ion. So we would say that we would have 99 molecules of acetic acid, and then we have 1 hydronium ion, and we would have 1 acetate anion. So that's the kind of thinking that we're going to apply to concentration. So next, we're going to start with an initial concentration here. And we're starting with a 1 molar solution of acetic acid. So I can write here 1.00 as my initial concentration. And just like before, we're going to pretend like nothing has happened yet. So the concentration of hydronium is 0, and the concentration of the acetate anion is also 0. So next, we're going to write a C here for change. All right, and let's define X as the concentration of acetic acid that reacts. So if we have a concentration of acetic acid as being X, let me go ahead and I'll just write X here. That means we're going to lose a certain concentration of acetic acid, and therefore we're going to gain the same concentration of the acetate anion, and we're going to therefore gain the same concentration of the hydronium ion. So when everything comes to equilibrium, so our equilibrium concentrations would be 1 minus X for the concentration of acetic acid, and for the concentration of hydronium we would have X, and for the concentration of acetate anion we would also have X. So now let's write our equilibrium expression. So let's get a little more room down here. So our equilibrium expression, so Ka would be equal to concentration of hydronium ion, so the concentration of hydronium ion, times the concentration of acetate anion, right? And this is all over the concentration of acetic acid, and we leave water out. So all over the concentration of acetic acid here. All right, let's plug in what we know. So the equilibrium concentration of hydronium, that's X, right? So that's X. So let's go ahead and put that in here. So we can put X in for concentration of hydronium. And concentration of the acetate anion, that's also X, right? So that's the concentration of the acetate anion. So I put in an X here too. All over the concentration of acetic acid. At equilibrium, that's 1 minus X. So I put in here 1.00 minus X, and this is equal to the Ka for acetic acid. All right, so we had that on our table above, so let's go back up here to the table that we talked about earlier, and here is the Ka for acetic acid, 1.8 times 10 to the negative 5. So we plug that in. We plug that in here, so let's plug in 1.8 times 10 to the negative 5. Now, at this point, you could solve for X, but you would need to use the quadratic formula. So let's make an assumption at this point, and we're going to assume that X, our concentration, is much, much smaller than 1 molar, because that makes our life easier for the math. Because if X is much, much smaller than 1 minus X is approximately the same thing as 1, right? Because if this is an extremely small number, subtracting it from 1 isn't going to do anything. Isn't going to do much of anything. So we're gonna make this assumption and say that 1 minus X is equal to 1. And that just makes our lives easier. So now we have 1.8 times 10 to the negative 5th is equal to X squared over 1. So all we have to do now is solve for X. So let's get out the calculator here, turn it on. So we just need to take the square root of 1.8 times 10 to the negative 5. And so we get 0.0042. All right, so let's go ahead and write that down here. So let's get some more room. And X is equal to 0.0042. And remember what X represents. X represents the concentration of hydronium ion, right? X here represents the concentration of hydronium ion at equilibrium. So this is equal to our concentration of hydronium ion. And now we can calculate the pH, which was the whole point of the problem. Right? So let's calculate the pH of our solution. So the pH would be equal to the negative log of the concentration of hydronium, so the negative log of 0.0042, and we can use our calculator for that. So let's go ahead and take the negative log of 0.0042, and that's going to give us a pH of 2.38. So let me go ahead and write that. So our pH is 2.38. So that is the pH of our vinegar solution.